Cool. Thank you very much for the invitation, everyone, including Ian, also invited me. We work in the same place. So yes, I work at the Center for Advanced Study of Collective Behavior at the University of Konstanz and the Max Planck Institute of Animal Behavior. It's a very beautiful city, and you should come visit us. Okay, so today I'm going to talk to you about one of the things I have been very excited to work on, which is the problem of foraging. And if any one of you have been to New York City, knows exactly the heroes of New York City are this very nice rats. You know, they carry a pizza. The guy looks back. Should I take this pizza slice or not? And this is a behavior that we all do, which is to forage. So almost all animals, I would say all animals, self-sustain through acquiring energy and search for food. It's a universal behavior. It happens on a multiple spatiotemporal scale, so you can study it in the lab in a small box or out in the field. It is sensitive to the environmental structure, so depending on the structure of the environment, animals adapt their foraging strategies in order to survive in an environment. And as somebody who was very interested in modeling, is really, it has a long, foraging has a long history of being quantitative within behavioral ecology. Just to give you another pizza rat video, 1 minute, because okay, so I'm showing a lot of videos because I have a running project now in New York City where we track rats in subways and in Central Park. So if you want to join efforts, you can contact me, but that's not what I'm going to talk about today. Okay, so just to dive in directly, and today just to give you the idea of my talk, I will begin from a microscopic single agent model and begin to build up, and I hope we can reach till the end. So the foraging problem I'm very interested in is the patch leaving problem, okay, which is pretty simple, looks simple, that you have an animal, here I'm just having my rat, go into an environment that have resources, patch resources, and then go in, exploit some resources, and then leave to the next patch, and so on and so on. So the behavioral observables that you have here are the patch residence time, okay, is how much time I spend in a patch, the travel time, okay, the time I take to travel between patches, and how much food intake within the patch. Within behavioral ecology, there is, so you might have heard on optimal foraging theory, there is something called the marginal value theorem. Okay? So the marginal value theorem, it proposes this rule of thumb that the animals leave its patch when its current patch intake rate is equal to the average environmental intake rate. And if you look, it was like established in around the 70s, and in many papers you will find this kind of curves where you have the cumulative resource intake plotted against the time foraging in patch to get the optimal time in patch. But if we go deeper, we find that the marginal value theorem have very strong assumptions underlying it, is that the animal knows basically everything about the environment, the food is arriving continuously, and this environmental statistics remain unchanged. So these are very strong assumptions. Throughout the talk, I will use MVT as a guiding principle and a measure for comparison. And when I was searching for, okay, where to begin to pose modeling questions when it comes to foraging, begin to ask this following mechanistic questions. Okay, how, even if, let's say, the marginal value theorem holds, how would the animal implement it? It doesn't tell me how would the animal implement it. What happens if there is stochasticity both in the environment or in the foraging process itself? Of course, the basic question of how does the animal learn the structure of the environment, and whether we can extend it to social foraging. So throughout the years, I have developed modeling frameworks to address these questions, and today I will really focus on two, which is here in red, on this Bayesian approach to foraging, and how we can extend the foraging models from a single agent that is doing integration in its environment to a bigger social group. Okay, so just to get us started, Bayesian approach to patch foraging, which I'm sure Bayesian approach will be very familiar to almost all of you, is you accumulate the statistical evidence, in this case here, about the patch or the environmental quality. And within behavioral ecology, there have been quite a long history of trying to look, okay, do animals use Bayesian updating? Do they forage like Bayesians? But the models that were developed in behavioral ecology were not very systematic. And for me, as somebody who is very interested to either to investigate the neural dynamics or look at motion, it's very hard to relate it to this realm. So let me explain more clearly what do we mean by formulating foraging as a statistical inference problem. So I usually, there will be a lot of math in the talk, but for me it's very important that we get the intuition behind this model. So let's say we have an animal, whatever you believe, thrown from the sky, okay? And it has to solve two problems. First, it has to find a habitat, okay, the habitat choice. And once it finds a habitat, it begins to exploit this habitat. So the habitat, you can think about it as a proxy of a non-depleting patch, so like a big forest where the food doesn't decay over a long time. And once I find the good forest, I begin to exploit within it, which can be approximated as a depleting patch. And the statistical inference routine I'm talking about here is that the animal, for example, have a prior over how rich a patch is. Okay, I have a prior. I go into a patch. It has some food density. I encounter the food, and then I update my belief, constructing a posterior probability, which can be written in the known Bayes rule. And then if you look, for example, if you look at the maximum likelihood of this rate over a long time, you can approximate the true underlying rate. Okay, but that's not enough. We wanted to look at what the animals, the decision strategies that the animal are doing. So let's tell you again the philosophy of the modeling I'm developing. As somebody who are trained both in physics and neuroscience, one part is we want to look at the cognitive mechanisms that the animals might be employing in different environments, and then begin to scale it up into larger number of individuals. So let's look at the habitat selection problem. And we said that the habitat selection can be approximated by having non-depleting patches. So let's say I have 3 richness here. That's a very rich habitat, a bit lower, and a poorer habitat. Okay, so let's think together, how would the animal try to solve this? Okay, I keep searching, and then over time, I realize that this is a non-depleting habitat, and I will remain there forever. So maybe what the animal is doing, I will try to do in this case, okay, animal, I mean, conceptual animal, that it's try to minimize the time to find the high-yielding patch. And whenever I have this habitat more obvious, the easier I will find it. Okay, can we get this from the model? So here I will treat the simplest problem, which is if we have a binary environment, okay, we solve it for ternary and more, that have high, let's say, has the high food arrival rate, low food arrival rate with certain probabilities. So you can write down the stochastic differential equation of the belief, where you have here y your belief variable, and you have 2 terms, one that account for the food encounter and one for the lack of food. And the best way to represent this is to look at it pictorially, looking over time. If I begin with my belief here, I'm in the high patch, move to the low patch, move to the high, move to the low, and I keep doing this till I leave asymptotically the low patch and stay in the high patch. Okay, so here what we are proposing is that the animal is doing a sequence of staying good decisions, and it leaves when it crosses a certain threshold. And we can basically, by looking at the first passage time, we can basically compute this times that we are trying to minimize, the arrival time, which depends on a couple of parameters. Most prominently, the probability of the high patch, okay, and the escape probability from the high patch, and the transit time, which is tau between both patches. Okay, so let's try to do some simulations and look how our analytics and simulations work. So that's another disclaimer. Also, what is guiding the choice of models is that I try to simplify things in order to get at first order analytical tractability. So here we look at the arrival time if we keep the low rewarding patch constant and we keep increasing the high rewarding patch, we are minimizing the arrival time. We can play the same game by keeping this ratio, which is the discriminability between the high and low patch, and increase the probability of the high patch in the environment. We are minimizing also this arrival time. But what else? So the nice thing about this type of models, this accumulation of evidence models, is that there are parameters that we can infer that are not observable from the experiment, which is this optimal threshold that we can observe by fitting it with the data. And here we can see that this optimal threshold decreases with discriminability, which is this ratio between lambda h and lambda L, as there is evidence is accumulated more quickly. Okay. So what we are proposing here is that our virtual animal here might have an algorithm in its brain trying to solve this habitat selection problem, which takes the log likelihood ratio of the high patch to the low patch. But let me then say, okay, what happens if I just change a small thing about this environment? Once it finds the habitat, you have depleting patches. So what happens if I have a depleting environment? Just this one parameter, and instead of the patch replenishing all the time, I have a depleting environment. So let's think together. That's a scenario closer to the marginal value theorem, a scenario where the animals that I have a rich environment, lower and much poorer, the animal will keep sampling from this environment and then will tend to stay more in the richer environment. If I have no uncertainty, if the animal knows the structure of the environment, then basically the strategy will obey the marginal value theorem. But if I have an uncertainty, the forager strategy will deviate from the marginal value theorem prediction. Let's see systematically how this happens. So in this case, in the depleting environment, what we are proposing is that the animal is not really optimizing the time to arrive, and the high patch is doing what one would expect, which is to optimize the long-term reward rate. Okay, how do I optimize my long-term reward rate if I have different, for example, in this case, in the binary depleting environments? Okay. So in the binary environment, if there is no uncertainty, we are able to recapitulate fully the marginal value theorem, which is I will leave, the optimal strategy is to leave when my own rate high is equal to the rate of the environment. But what happens if I have an uncertainty in the environment? So how can I model here the uncertainty? Is by looking at, I have a certain amount of food in the patch, and I keep making this amount of food very hard to infer, which is lower and lower number of food patches. So at the very large number of food chunks, the animal in its patch residence times will approximate the marginal value theorem predictions. But as I decrease the amount of food chunks significantly, there will be deviations. Okay, what are these deviations? That the animal will stay in low patches too long, which is called overharvesting, or will leave the high patches too soon, which is called underharvesting. Okay? So I'm going through it a bit faster just because that's a single animal strategies. But here we see that we change just one thing about the environment, which is that it is depleting. Okay? And then we're able to change the strategy, the optimal strategies that the animal might be using. Here, it is doing a maximum likelihood estimation over the food arrival rate. Okay? So just by changing, again, in the previous, when we had non-depleting environments, it was doing a log likelihood ratios over the high and low patch, and here is doing maximum likelihood estimation. And if we have uncertainty, okay, the forager will underharvest high, but will underharvest the high patch or overharvest the low yielding patch. And the overharvesting is a ubiquitous observation in the data. So just to recap here, if you haven't been paying attention to me at all, that we have this modeling framework that it accumulated evidence using evidence accumulation. So just if you have missed the idea of evidence accumulation, I just want to clarify it. So, because I think I went a bit fast. Okay, sorry for my drawings, but that's a rat enters here, and then you have food, okay, inside. And then let's assume that this animal in its head had a variable accumulator, which is a decision variable, begin at 0. And then when it is eating, it receives an evidence over time. And then this evidence makes it's a noisy process because it's a drift diffusion model till it crosses a threshold. And this threshold is this boundary here to leave the patch. Okay, and this is a drift diffusion model. Because we will use it in the next part. So what the animal is doing is this type of an normative evidence accumulation model, which can be derived using normative Bayesian approach. Okay, we have also shown that the existence of uncertainty really deviates the animal from optimality. Okay, so what happens if we extend this to social foraging? So what we are doing with social foraging is we said, okay, let's then extend this framework to social foraging. Is that if you have two patches, okay, and then we have multiple animals, whatever you want. And then let's say that this is a poor patch, and this is a rich patch, and then the animals will be moving between them. You have here TR, the travel time, okay? And let's first look at what happens if you have a lot of animals, but they are not interacting, the non-coupling, okay? Not coupled. And we can write down the drift diffusion equation, which we have seen in the previous talk for this. Like we have a decision variable here, we have a reward function, we have our drift term, and then our noise term. And then if we simulate this, we get this type of dynamics that, okay, I am accumulating evidence, leave, then go reset, go to the next patch, accumulate. And then here you see this is wider in the rich patch. Sorry, it should be wider in the rich patch because I spend more time in it, and narrower in the poorer patch. Okay, so this is the equation for this. Okay, what do we do? Okay, can we then we can compute the full probability distribution analytically by integrating the previous equation from 0 to the threshold, and we get this inverse. This is an inverse Gaussian distribution. Okay. Which is this, we can get the full probability distribution. But okay, if you want to get exactly the probability of leaving the patch K at time t, we convolve this and do some tricks, and then we get this equation here. And we can get also the probability to be in the patch. So you see the logic here. We compute the full probability distribution, and then we can get the probability of leaving patch K at time t, or the probability to be in the patch. And what is very interesting is that we get these oscillations here. So these oscillations mean, so here we have, for example, this is P0, is one of the patches, which look here at the probability of leaving the patch. The orange lines are our analytics, and then the violet is the simulations. So what is this oscillations means is that it means that the group is going back and forth, and then at the end, it reaches an equilibrium distribution among patches, okay? In this patch. So there is a fraction in one patch and fractions other patch. So they keep moving. Okay, I leave and leave and leave, and then there is an equilibrium distribution. Okay, so that's to give you more the intuition of how I'm developing this. So next, oops. Yeah, shout immediately. Yeah,
so the social is not that they're learning from each other, but that the patch is being...
No, there is no social here.
Oh, okay, gotcha.
These are non-interacting, and then I will introduce the interactions. So
Right.
I just slowly working it up.
So the oscillation is just because they all start on one patch?
Yes. They are just moving. And then I had this non-coupled situation to compare it to the coupling. What will happen then if you have coupling?
But are the patches resources being...
It's a non-depleting.
Oh, okay.
It's a non-depleting case, exactly. And non-depleting case, we have the deplete. So, okay, the non-depleting is analytically tractable. The depleting, then things get a bit murky. But I have the simulations for it. I can show it for you. Okay. So, what happens next? We can just, again, this is a non-interacting case. We can compute this equilibrium probabilities that we shown here. Okay, what is the equilibrium I reach here? And then they depend on this effective, most prominently this effective drift term. And then we can see, okay, let's see if our intuition hold. Okay, if P1 is much richer than P0, so the probability of leaving, let's see, okay, sorry, I always confuse, sorry. So here, if you, let's look at this. So if I have the P1, which is how rewarding this patch is, it's much more rewarding than P0. So the Q equilibrium is at this, okay? And then the same is here. And here we look at the travel time. If I increase the travel time, this affects also my equilibrium accuracy, which is, this is the probability to be in the patch. Sorry, I just got confused here. The probability to leave the patch, and here is the probability to stay in the patch. Cool. So, and then you saw these oscillations here that I mentioned. Okay, they keep moving back and forth till they reach the equilibrium. So we can compute something called the damping parameter, which is this parameter here. And then this parameter, the smaller this parameter is means they are the oscillations is decaying much faster. Okay? Cool. So again, reminding you, what are the parameters we computed? We computed this probability to be in the patch, the probability to leave the patch, and this damping parameter, okay? Because these are the parameters that are gonna change depending on the social coupling that we are introducing. Okay. So what type of social coupling? Okay, so let's here come to your question is we introduce social coupling. So there are many ways we can introduce this. So let's imagine, okay, I'm in the patch. How can I couple with the animals? So one thing, I can do a diffusive coupling, which means I follow the belief of my another animal. So it's like kind of a mind reading. Or pulsatile coupling, meaning if I see an animal leaving, then I follow that couple, or I see it arriving, then this is another way to do this pulsatile coupling. The reward coupling, if I see another animal getting a reward, then that's another type of social coupling. Another one is counting. I see how many animals are in the patch, okay? And then we can use the same drift diffusion model that we use, but introduce a social coupling parameter term. And then we can write them down. We can write down the reward coupling, and then the diffusive coupling, pulsatile coupling, either D here for the departure or the arrival, or the counting. Okay? And then begin to repeat exactly the same simulations we did before, but with this coupling. So we see here that if we do a reward coupling, which I see other animals getting a reward. So here, this dotted line is a non-coupled case, okay? And then this is the case where there is the reward coupling. So we can see what happens is that in this case, we have this Q1 equilibrium increased. So the probability, okay, to be in the patch increased in the richer patch, which is number 1, okay? And of course, the residence time, the average residence time in this patch increase. But what we can see most prominently in this damping parameter decreased very significantly, which means that they reach the equilibrium very fast. Okay? And then we can play all kinds of games here. We can increase.
Can I just,
Sure.
Just to make sure I fully understand. So in the previous equations on the previous slide,
Yeah.
is capital N the population size?
Yes.
So each individual is aware of the entire population size?
Yes, for now, yes.
Yes. But you'll relax that later? Or?
Yes. It's it's relaxed in the paper I'm relieving, but just again to get the analytical curves, but it's relaxed. You can relax it with. Sure. And here we can play all kinds of games. Is that if we increase, for example, the QR, which is the coupling, the strength of the reward coupling, we can increase this equilibrium probability to be in the patch, and we decrease, of course, the probability to leave. And the more we also increase the strength of this reward coupling, we are dampening more the oscillation, so it's very fast for them to reach equilibrium. Let's see what happens if you have this diffusive coupling. And again, this will be relaxed later, but I take that it's perfect diffusive coupling, again, for tractability. We see that, okay, we have this dotted curve is the non-coupling case, but what happens is we don't see any change either in the probability to be in the patch or the patch residence time. This is the probability to be in the more rich patch or the patch residence time in the rich patch. We don't find any change in this parameter. What we find really changing is this damping parameter increase, and I think it's just a bit non-intuitive. The damping parameter increase means that you see more oscillations here, meaning because of the perfect belief couplings, they are going back and forth more. Okay, because they're more cohesive, they want to stick together more. And we see that this scales with the number of the group, with the number of agents we have in the group. If you have hundreds, then this parameter increases. Okay, we can do it again with the pulsatile coupling. And here, in every time we write down, we have equation for the effective drifts that comes from this coupling. So with the pulsatile coupling, you have two scenarios. First, if I observe arrivals, if I'm coupled to the arrival of others, what happens is the equilibrium probability to be in patch 1 increase, along with the patches this time, but also this cohesiveness increase, which is this damping parameter. If I'm paying attention to the departures, okay, which will tend to couple you to move earlier, so the probability, equilibrium probability to stay at patch 1 will decrease, the patch residence time and patch 1 decrease, but still this damping parameter will increase compared to the non-coupled case. Okay. So the counting. So in every slide, I'm not going through how we derived the exact coupling, but we have to get this effective drift, basically, that happen with which we do the simulations or the analytics. And here we find a very interesting thing is that we find that our equilibrium probability to stay in the rich patch increase, the patch residence time in the rich patch increase, and the damping parameter decrease, meaning that they reach the equilibrium very quickly. And we can play here the same game. We increase this counting coupling, okay, but as we increase it, we increase the probability of the equilibrium probability of being in the rich patch, which is patch 1, and decrease the leaving probability from this patch because they are inverse to each other, of course. So here just I give you an example that, okay, that if we take the previous model, which is an evidence accumulation model for a single animal in a patch, and extend it to a group of socially interacting agent, we can get some collective stability, which is this equilibrium state after an oscillating period, okay? So, and then we can, by changing the information sharing mechanisms between those animals, we can get different social dynamics. For example, if I couple them with reward, which is this QR, I can decrease the cohesion of the group, which here we mean decreasing cohesion means that you reach very quickly the equilibrium, so you have rapid redistribution to both patches, so they means they don't stay together for a long time. The fraction in the best patch increase. The diffusive coupling, we increase the cohesion, and the fraction in the best patch doesn't change. Same hold for the pulsatile coupling. If I pay attention, if I couple so that the departure of other agent, my cohesion increase and the fraction in the best patch increase. In the pulsatile case, if I'm paying attention to the arrivals, I increase the cohesion and the fraction in the patch increase. With the counting, my cohesion decrease and the fraction in best patch increase. So here you notice something very interesting. So why is everything increasing here? Because there is something I didn't tell you in the beginning. I said it, but I said first it's an egalitarian structure, so all individuals are the same. And the second is cooperative couplings. Okay, so, and this will lay the foundation for the next phase of the work, which will take into account, okay, what happens if I have social hierarchy? So if I have leader and follower, like we heard in the previous talk, so I have leading and I have followers, then here you can say, okay, in the pulsatile case, this animal, and this goes to Ian's question, this animal pay attention only to the leading, but the leading doesn't pay attention to the others. And then you can play all kind of games. For example, in the diffusive, you can say, okay, I am doing the accumulation faster than you. And then we have also a couple of other scenarios you can think about, which is stealing food. Stealing food here will mean that the reward coupling will be negative, or sabotaging, so the anti, here I decorrelate your accumulation process, which will be like propagating false beliefs. So the nice thing about this type of modeling is that we can add details over details, and it provide a very flexible framework to build on. Of course, not analytically when we complicate things, but at least in terms of simulations, we can be pretty close to experiments that we are currently doing. This is the first point. Yes? Yes?
So, I don't know a lot about animals, but what little I know about social hierarchy is that the alpha rat is not going to try to lead other rats to a good source of food. It's going to chase them away.
Yes.
So we've modeled that.
Yes, I think the stealing the food will be the one thing. Or you can say anti-pulsatile is not that they are not leading, but it's like a negative correlation. Like if I'm leaving here going to the high rewarding patch, I will send a coupling by saying stay there in the poorer patch. That's one thing. But it's open to all kind of. So the idea is to have a very flexible framework where we can add, whatever mechanisms you have, and then more locally, how many you can go into whether you send your coupling locally or globally. That's another thing. So. Yeah. Okay, another thing you notice that I didn't really talk about the travel time. I didn't talk about how they move in the middle. So these models are all time. There is no space, okay? So how do we introduce space? that's where, I have some ideas, we can discuss it if people have. Like, I recently was in a student in a course in physics of active matter to revive my active matter knowledge. Is that, we can treat them as like, okay, you have the animal as some active particle, and it have some, let's say it begin as Brownian motion, and then over time, okay, you accumulate something from the environment over space, and then you reduce this angle that you are moving. So you have some directed motion, like the motion models we saw with drift and diffusion. So you have a spatial integration process, and then you can try to couple it with this type of models. So that's one idea. Another thing that I'm working on is continuous evaluation. So let's say, okay, the whole thing about patchiness. The question is that, okay, do animals perceive the environment at all as patches? One can say, okay, if you see a big forest, it looks like a patch, and you have more trees here, more trees here, more trees there. But what happens is if you have a continuous environment. So, and here the abstraction that I'm trying to get at is, the simplest thing to say is the animal is moving on some potential, and then we can look at the integration, is it integrating the information over gradients, which is like work that was done in chemotaxis or other, like infotaxis, also the more generalized version of it. But again, algorithmically give me a very general model, but it doesn't tell me how the animal is implementing it. So we will take it as a point of beginning. Okay, if we have this continuous environment, how can we get into strategies in terms of, okay, I sample the local information and leave these areas that have a certain gradient. Okay, so that's where I'm going. So just I thought that to have the slide just to give you insights into how I'm using this modeling framework, beginning from a single animal going into a larger number of animals. And then, of course, at the end, how do we apply this to data? That's a whole can of worms. So we tried with a simple like social evidence accumulation model to do model identifiability, because if you want to take some of these models and fit it to the data, it's not very clear how you do this. So first you need to look at whether the parameters are identifiable or not. We can go into the routes that I simulate the model and whether it looks like that or not, but that usually doesn't really convince me. I think we should try to like fit the models to the data, but then it's really not very trivial, but we are getting there. So the advantage of being in Konstanz is that there is so much data that one can work with. And the idea is to get insights into this type of latent variables, like, does animals have this type of like accumulator variables that is accumulating evidence from the environment? And more interestingly, can we infer this social couplings or not? So that's basically what my group is trying to do. So just not to be on time is, yeah, it's on time. So I acknowledge, so many people I worked with, either in Princeton where I did my postdoc, and so many collaborators at the Max Planck Institute of Animal Behavior and University of Konstanz, and all the funding. And before I finish, we organize every year a School of Collective Behavior. That's a 2024 advertisement, but it will be organized during the same date in 2025. You come for 3 weeks, and it's like collective behavior on steroids. So it is targeted to people from quantitative background. You have lectures, you do projects, and you swim in the lake. So thank you very much for the invitation.